Hello everyone, welcome to the Engineer Your World Return to Venus presentation for SEAS 2023. This year, our team has tackled the challenge of designing, building, and testing an entry, descent, and landing system for atmospheric and surface data collection on Venus. Our team consists of 10 people, but to increase productivity, we split into 2 teams of 5, Team Alpha and Team Sigma.
This is our mission patch. Its V-shape represents Venus and our visionary mission, and the design itself displays Venus, Earth, and a distant exoplanet, similar to the exovenuses we hope to utilize our research to study. Now we will introduce members of our team from all across the country.
Hi, I'm Andrew Chichester, and I'm from New Jersey.
Hey, I'm Ethan, I'm from Pennsylvania.
Hi, I'm Fiona Mateo, and I'm from Florida.
Hi, I'm Jervis Benjamin, and I'm from Minnesota.
My name's Tiffany Palm, and I'm from Oklahoma.
Hi, my name is Aaron Lee, and I'm from Nevada.
Hi, I'm Enzo, and I'm from California.
Hi, my name is Harley Woltz, and I'm from Ohio.
Hi, I'm Siyona Jain, and I'm from Texas.
Hello, my name is Zoe, and I'm from Missouri. Before we even started designing, we outlined a few mission objectives to guide us in our process. First and foremost, our main goal was to descend through the Venusian atmosphere as slow as possible to maximize data collection and learn more about its composition. Next, our goal was to explore the Venusian surface. Exploring both the atmosphere and the surface are particularly important because we have very limited data on either of these planetary aspects. Additionally, as with almost any planetary exploration mission, we wanted to check for any possible signs of life. And finally, the visionary goal of our entire mission was to apply our findings to understand the history of Venus and implications in the search for exoplanets.
To begin the brainstorming phase, each of our team members researched past missions to Venus and explored what worked, what didn't, and why. We each sketched 3 original designs, some of which are shown here. Our ideas included planes, gliders, capsules, and rovers, with aspects like parachutes, balloons, motors, and more. The range of ideas in the creative design phase was incredibly diverse because we had few restraints. After completing our designs, we reconvened and shared our ideas with our subteams. Each member analyzed the team's proposals and provided constructive criticism to better the blueprints of our peers' EDL system. Using our teammates' comments, we ultimately worked to create a personal final design. The next day, we each pitched our final ideas to our teammates. Combining the best aspects of each design, we finalized our sketch to scale for the prototype probe we will be working on for the next 2 weeks. In this process, we also focused on researching viable materials that could withstand the Venusian atmospheric conditions and implement them into our spacecraft.
The prototype for Team Alpha consists of a powered glider and a probe, which together could provide a more comprehensive analysis of Venus's atmospheric composition across various altitudes. Since the upper layer of atmosphere is slightly less extreme in comparison to the deeper layers of Venus, our team figured that a craft could stay there for a more prolonged period of time, while also having access to solar energy. As a result, we decided on a solar-powered glider with Teflon-covered solar panels that would ride the upper atmosphere, analyze dust particles in the high atmospheric layer, and use imaging technology to remotely peer into the deep atmosphere and surface. Since the solar-powered glider would be inefficient to fly in the lower atmosphere, the glider would then deploy a small probe which would fall into the deeper atmosphere so that a more in-depth study of Venus can be made. This small probe would initially use a Teflon-coated parachute to slow its descent, and after the chute became inefficient, the probe would cut the strings and rely on its drag fins to further slow down in a deeper layer. This design, where the 2 crafts are specialized for 2 different parts of Venus, allow us to study Venus as a whole while being able to operate for a more prolonged period of time. Now moving on to Sigma Team's prototype.
Our initial team design consists of 3 stages: a descent module, a lander, and a balloon. The descent module consists of a hexagonal pyramid capsule made out of titanium and protected on the bottom by a heat shield created with heat TPS material. Later, the heat shield is jettisoned and the trapezoidal sides of the capsule deployed to form air-braking fins which decelerate the vehicle to about 0.155 meters per second at a mass of 1,000 kilograms. As the craft falls, a Teflon-coated superpressure balloon inflates and detaches from the capsule, measuring elements of the atmosphere and adjusting altitude through a dual balloon system. Once near the surface, small rocket engines located near the fin tips fire and slow the vehicle down to a standstill midair, from which a lowering mechanism akin to the sky cranes of the Curiosity and Perseverance rovers places the spherical lander onto the ground, cuts the connecting cables, and flies away from the lander.
Originally, the descent stage design utilized a hypersonic inflatable aerodynamic decelerator, or HIAD, along with holding claws for the lander. However, in consideration of the thick atmosphere of Venus and the concerns with the lander falling out of the descent stage too soon, a normal ablative heat shield and a sky crane mechanism with a cable were used instead. The lander itself has a main pressurized body made out of titanium inner and outer skins, with an aerogel insulated fabric in between. Inside the pressurized body, a hemisphere with a low center of mass moves around using 2 wheels in contact with the outer sphere, allowing the entire lander to roll around in similar function to a sphero. Around the outside of the ball are several gates through which an instrument pole can extend from the inside of the craft to expose sensors to the outside Venusian environment, retracted after sufficient data collection to cool down in the controlled environment of the sphere.
Next, we started building. Creating a physical prototype from a conceptual design involved multiple intricacies. Yet through a challenging and sometimes tedious process, we ensured that the collaborative effort among our team prospered. Whether it be reshaping certain dimensions of our decelerating fins or expanding the width of a parachute, building our models allowed us to test our theories, see where we went wrong, and make adjustments.
As mentioned, Team Alpha constructed a prototype glider, probe, and parachute over the course of several days using a variety of materials such as foam board, foam sheets, string, and trash bags. Although our EDL model primarily consisted of makeshift materials like duct tape or foam board, the actual spacecraft for Venus will be composed of more sophisticated resources. To start, the fuselage of the plane will be built out of titanium. Titanium is an ideal material for spacecraft, not only because of its durability, but also for its resistance to corrosivity. The propellers of the glider will be made primarily from aluminum to maximize durability, and reinforcing them with nickel may also be helpful for excess safety precautions against atmospheric conditions. Shortly after ejecting from the dropship, the probe will deploy a large Teflon-coated parachute. Teflon will ensure that the parachute is protected against the sulfuric acid layer and Venus's hostile composition. Yet, upon all this search for materials, I came across two exceptional and recently discovered materials that are perfect for our capsule. Though expensive, tantalum and hafnium carbide can withstand temperatures up to 4,000 degrees Celsius, and they possess a durability unparalleled to previous resources. Outcoat tiles, also used on the Orion mission, will be incorporated into the heat shield as they are believed to withstand heat up to 5 times Venus's hottest recorded temperatures. As for sensors, the probe will have a dust mass spectrometer to determine what the Venetian dust is made out of, an ultraviolet and visible light spectrometer to determine the atmospheric composition by analyzing light, a thermal emission imaging system to distinguish variations in temperature, an accelerometer to allow for greater control while descending, and a Vendy camera to take infrared images of the surface. Here are a few videos displaying the testing of our spacecraft. Not only was it incredible to see our prototypes come to life, but also succeed in their goals of slow descent and atmospheric flight. Building our prototype was fairly straightforward, but definitely time-consuming. We had created blueprints, so we knew what the design was supposed to look like, but the most challenging part of this was figuring out how each material and design interconnected. You can see photos here of our build process. Some of the materials we used were corrugated plastic, cardboard, and fabric for the atmosphere module, and fluorofoam, wooden rods, and a styrofoam sphere for our lander. We also attempted to incorporate servos and motors to make the prototype more realistic.
Here are a few videos and images of our prototype test. We went through a total of 3 tests. The first was just for the fins alone to ensure they worked how we envisioned. Next, we attached our hardware and the landers stand-in. This test ended up failing due to the lack of supports to prevent our fins from bending 180 degrees. We went back and reinforced the top with rigid dowels to prevent our fins from flipping back. This resulted in our final successful test.
Throughout our design process, we were fortunate to be able to meet with 3 NASA subject matter experts to discuss our mission with. First, we met with Dr. James Garvin, the principal investigator of the Da Vinci mission at Goddard Space Flight Center, who gave us insight on what materials and data we should use so that we would be able to effectively study Venus as a whole. Next, we met with Jeffrey Balcerski, a planetary scientist at Goddard. We discussed the landing site, Venetian atmospheric conditions, and replicating Venusian environments. Last, we met with Dr. Jeffrey Hall. He's an associate directorate technologist at NASA JPL. He and his team are currently testing a design of thin metal balloon coated with a Teflon, which in the Venusian atmosphere will allow for a much longer phase of data collection. Self-pressured balloons are one way to collect more data in the atmosphere by transferring gas between the balloon and the helium tank to pressurize for the specific layer of the atmosphere that it is placed in. Being able to stay in long periods of time in a specific atmospheric layers is fundamental to collecting lots and lots of data over extended periods of time.
After we compiled our research, we determined the landing site. Our landers will explore the northern areas of Venus due to their unique geological features. Our plane will fly at about 7 to 10 kilometers right between the atmosphere's supercritical fluid layer and cloudy layer. This will enable us to take the best quality images of each site we will visit, of which there are 3, those being Cleopatra Crater, Lashimi Planum, and Fortuna Tessera. Fortuna Tessera has one point of interest because it is one of Venus's oldest geological features and presents incredible opportunities to investigate the history of Venus. Our glider will first make 3 imaging passes over the western parts of Fortuna Tessera before dropping one of 3 landing crafts over the site. Upon impact, our spacecraft will begin up-close imaging and analyzing of rocks in the area. Another designated drop site is Cleopatra Crater, an impact crater near the summit of Maxwell Mons. This crater is about 2.5 kilometers deep and 100 kilometers in diameter. The glider will complete 4 rotations above this site before ejecting its lander into the crater. Our lander will explore the layers of rock exposed by the impact. The last drop site, Lashimi Planum, is a plateau about 5,000 meters above the Venusian surface. Cursory images of this site from other orbiters have revealed that a sizable chunk of this site is composed of lava flows. Lava flows are of particular interest to our lander because investigation of the minerals within these lava flows can determine whether Venus was once Earth-like. The one major downside of this landing site is that its latitude makes it all very dark. However, using NiCad batteries, which we energize in the initial journey to Venus, we can power our plane and landers in darker times and places in the Venusian atmosphere.
Upon the approach to Venus, the powered glider will be released into the atmosphere with the 3 descent modules inside. In order to receive information from the landers, the data must be then transmitted to a spacecraft orbiting Venus, and from there it can be sent to the scientists on Earth. To do this, the landers will relay information to the power glider that will be in the upper atmosphere. The glider can then transmit that data to one of 2 crafts following an equatorial orbit around Venus. Between the orbiter from the Da Vinci mission and the orbiter that will be inserted as part of our mission, valuable atmospheric and surface data will be received every 40 minutes.
Now, for the results of the testing here on Earth. The first aspect of our testing was to examine the descent of our lander. At a 54-foot drop, the lander descended slowly at 1.3 meters per second for a total descent time of 13 seconds. This velocity translates to 0.016 meters per second in the Venusian atmosphere, and overall reached staggering success with fulfilling the goal of slow atmospheric descent for our spacecraft through the use of the parachute and its lightweight design. As for the powered glider, our team held various tests in an open field to test the stability and aerodynamic properties of our plane. We found that the control surface mechanism and ejectable hatch design were proven to be effective. We also made sure to focus on leveled and stabilized front wings, and that all wires and sensors inside the fuselage were connected for correct movement and a safe flight.
Overall, the glider achieved acceptable success through a meticulously engineered and aerodynamically optimized design. We observed the glider turning and taking off, and found that the glider is capable of sustained, controlled flight, while also being able to carry and drop a payload, such as the drone, at the same time.
Thank you, Fiona. Now moving on to Team Sigma's design. The initial aerodynamic tests with a hexagonal capsule design were successful. We dropped the capsule from the 4th floor of the CSR building, and it performed very well. The video of the drop is shown here. The descent flaps opened immediately after the drop and allowed the capsule to slow down dramatically. In the end, it took 4 seconds to drop, and the effect of the descent wings on its deceleration are obvious.
For the final design, the glider from Team Alpha and the descent craft from Team Sigma were integrated into a single craft, with a scaled-up foldable glider housing 3 descent craft in a cargo bay, able to be deployed at particular points of interest. The heat shield of the descent craft is replaced by a simple fall-away cover protecting the base of the craft, and 2 drogue chutes deployed prior to decelerating fin deployment to prevent overstressing of the fins.
One of the many challenges we encountered during this project was designing around Venus's harsh conditions. Even though Venus is often referred to as Earth's twin because of the planet's similar sizes and masses, the atmospheric and surface composition, temperature, and pressure on Venus are contradictory to those of Earth.
Another challenge is that because Venus's violent conditions are challenging to manage, designing a lander that can survive these conditions and record data is very complicated with current widespread technology. Finally, designing a spacecraft for Venus's atmosphere but adapting it to test in Earth conditions was also difficult. Because we were unable to test our spacecraft in a simulated Venus environment, we had to make adjustments in order to accommodate Earth conditions like pressure, atmospheric composition, and temperature. Now on to our highlights.
Even though we faced many challenges, our mission delivered significant highlights as well. Our mentor was very kind in providing us access to almost any materials we needed. We participated in many hardware store runs and Amazon deliveries during our project building phase, and this almost unlimited access allowed us to design much more freely. Additionally, our team did a fantastic job collaborating with every member. We worked very well together, and each of us brought a unique skill set to the team. In addition to collaboration among all team members, we worked together in our subteams of 5, and even though each subteam was designing and building an entirely different system, we shared ideas and used other perspectives for our advantage. Finally, our ultimate prototypes were very functional. Even though we did not have access to hundreds of thousands of dollars worth of materials and technology, we were able to create some amazing prototypes with many functioning parts.
For future missions to Venus, new innovations in both material sciences and spacecraft developments will be imperative in creating larger, greater, and more in-depth missions. First off, gliders can cover and explore the entire upper atmosphere extremely quickly and effectively. A glider is also easier to steer compared to a balloon, which means we can control it to remain within a certain distance from our landers and maintain contact between the ground and the space probes to maintain communication. Next, landers that roll by displacing their weight would be great to create a never-before-seen traversable lander. Emerging materials and technologies suited for harsh conditions of Venus would allow more freedom to explore its surface. The ability for crafts, especially for a glider, to take advantage of both solar and extremely strong winds results in longer missions versus traditional fuel.
Now, looking at the applications of all our research. Understanding Venus is ultimately useful to fully define what it takes to be an exo-Earth. By redefining the lines of habitability, we can uncover if an exo-Earth is in fact more similar to an exo-Venus. Looking at the development of Venus to where it is today is the best window into looking for true exo-Earths. If we can successfully and fully understand how a Venus-like planet develops, we can limit the search of exo-Earths to what we know will contain long-term full habitability, resulting in a true exo-Earth. During a meeting with Dr. Jeffrey Hall from JPL, we discussed how many of the exoplanets we observe will be similar to Venus, since they'll be closer to their suns and easier to see. Because of the oncoming abundance of data on these exoplanets, it's important that we first understand a planet right here in our own solar system. Once we do that, we can apply those findings to exoplanets and learn even more about the origins of solar systems, galaxies, and the observable universe.
The feeling I got while working on our spacecraft, seeing everything come together, knowing that I could actually make an impact on real NASA missions, it was so cool and something I've never experienced before. That feeling has not only reaffirmed my career aspirations, but sparked new interest in other areas of study.
To me, NASA Seas hasn't just been an internship. Throughout these past 2 weeks, I've learned so much about myself and engineering. As my team and I have struggled through the problems of landing on Venus, I've learned so much about the values of exploration, experimentation, and teamwork. And this internship has driven me to be the best version of myself. And for that, I'm eternally grateful.
I am immensely grateful for the opportunity to collaborate with such a brilliant team and to expand my knowledge on relevant, hands-on research for a prototype mission to Venus. The opportunity to contribute to real NASA missions has been an unparalleled experience that has inspired and enriched my passions for STEM beyond compare. I leave the SEAS internship not only with further confidence in pursuing STEM research, but also with invaluable skill sets that I will carry with me for the rest of my career.
I'd be more thankful that I was chosen for this opportunity to collaborate with a brilliant team and to design and prototype a mission to Venus. Not only am I leaving the NASA Seas internship confident in my choice to pursue STEM and my abilities to conduct further research, but I have made invaluable connections with like-minded students and gained skills I will carry with me for the rest of my career.
I'm so grateful to have had an opportunity to do such challenging but rewarding work. I've always had an interest in aerospace engineering, but before SEAS, it felt like such a foreign concept. Now, the experience I've gained has made a career in the space industry seem much more attainable.
As my teammates have said, I'm incredibly grateful to be a part of the NASA Seas internship. I've designed airplanes in the past, but this is the first time I had the opportunity to apply my experience on a mission to another planet. I love the challenges that came with this unique mission, and I hope to continue my involvement in space exploration into the future.
I have been so fortunate these past 2 weeks to interact with people from such different backgrounds and walks of life, learning more about others and myself in the process of pursuing a challenging, significant, and exciting goal like designing an EDL craft for Venus. And I can say no more than thank you for this opportunity.
I'm extremely thankful to have such a unique and amazing opportunity to present my skills. I've always been one to build things and work with mechanics, but this gave me a chance to test my knowledge. SEAS has improved my knowledge about space and taught me things about engineering I never knew.
SEAS has left me with invaluable experiences and has allowed me to try new things and learn new skills that I have never been exposed to before. I am so grateful for the opportunity to speak with NASA and JPL scientists and engineers and be involved with such a hands-on project. I'm also so fortunate to have had an amazing and supportive mentor that facilitated our needs and supported our dream.
SEAS was an amazing experience to develop and apply my love for science and chemistry in a group setting like never before. Researching Venusian gases and compounds and then applying those findings to physical sensors, especially when trying to detect biosignatures like phosphine, adds a whole new dimension to something that I love. Being a part of this program introduced me to all sorts of people from all parts of the country with all different backgrounds in life, taking me out of my comfort zone and resulting in a truly irreplaceable experience. Thank you.
First and foremost, we'd like to thank our incredible mentor, Mrs. Hanover, for getting materials for us, setting up meetings with Venus subject matter experts at NASA and JPL, helping us learn about the engineering process, and assisting us in any ways we needed. We truly couldn't have done this without her, and I know I speak for all of us when I say she's amazing. We'd also like to thank the SEAS program for allowing us this absolutely incredible opportunity. We've all had so much fun over the past 2 weeks, and we've gained so many valuable skills in space science, engineering, research, collaboration, and the learning process. Finally, we'd like to thank you all for taking the time to listen to our presentation. We've had a lot of fun going through this journey over the past 2 weeks, and we appreciate your dedication to hearing our ideas. And now let's open up the floor for any questions you may have.